So today I wanted to talk about the LFP range of batteries from MG Energy. MG Energy are based in Holland and they manufacture basically two classes of batteries, some air-cooled lithium iron phosphate batteries, the LFP range, and then they have some liquid-cooled batteries generally for higher voltage or higher performance applications, which is the RS range, which I'm going to talk about in a separate video. There are three models within the LFP range from MG Energy. There's a 12.8 volt, 210 amp hour battery, which has got a stored capacity of around about 2.7 kilowatt hours. Then there's a 25.6 volt, 230 amp hour variant. That has a stored capacity of 5.8 kilowatt hours. And the largest battery in the range is a 25.6 volt, 280 amp hour battery, which gives you 7.2 kilowatt hours. So you may notice that both the 12 volt and the 24 volt unit there have a slightly higher nominal voltage than a lead acid battery. That is really of no consequence when you're looking at a 12 or a 24 volt system, and you can use them as direct replacements in systems where you would previously have had lead acid batteries. As you start to potentially series up these batteries, which you can, and we'll go into that in a little bit more detail further on in this video, then that slightly higher nominal voltage starts to multiply. So certainly, if you're using them in a higher voltage application, use the stated nominal voltage on the battery, and that will give you a much more accurate indication of what your nominal voltage is going to be at that seriesed up higher voltage. The MG battery works with a dedicated MG battery BMS, battery management system, and we'll have a look at that in a second. But let's start by having a look at the battery itself and the features on that. All of the connection points for the LFP batteries are on the top of the battery itself, and the terminal areas are covered by these removable caps, the black caps here. I've already removed the screws, so these covers just then remove once those screws are taken out to reveal our positive terminal and our negative terminal. An earthing point here, and a couple of data connections at the end of this raised center section here. You'll also notice that within the top of the battery here are a couple of grooves, and this allows you to address the cables that are going across the battery through the grooves. So if you were connecting, in this particular example, from the left hand side here, you could run the positive cable through the groove and onto the terminal, and the negative would dress away directly to the left of me. And if we look at the battery cap, you can see there are cutouts for cable routing, including a couple of smaller cutouts for the data cables. There is also provided a cap that fits over the entirety of the product. This is a rubber over molded product, and that means then we have a single seamless drip proof cover that will then sit over the entirety of the top of the battery. At the end of the battery we have two data ports. This is for CAN communication between the batteries and the BMS unit, and this allows the batteries to broadcast state of charge information, temperature information, and voltages of all of the individual cells. So it gives really granular data back to the BMS, and that allows the BMS to control the balancing of the cells within the entirety of the pack. All of that data is going back, and the BMS can now see which is the highest voltage or lowest voltage cell within all of the batteries that are connected to the BMS, and direct that balancing to occur to achieve an even charge across the pack. This particular battery has been specified with the RJ45 BMS connection ports. It is also available with an M12, which is a slightly more ruggedized connector. The M12 is mandatory once you're going above 100 volts DC as your nominal battery pack voltage, but for lower voltages you can elect to use either. The RJ45 is clearly a very cost-effective solution, and in the majority of our applications that's the one that we elect to use for lower voltage applications. In addition, there's a couple of LEDs just to give you some very simple status indication on the battery. When installing these batteries, it's very important that you torque the studs on these battery terminals to the correct level. It is actually printed on the top of the battery that you need to apply a maximum torque of 20 Newton meters. that doesn't feel that tight. But in the event that you do over torque it, there is risk of damaging components within the battery. So please ensure that you use a suitably accurate torque wrench to make these connections. So with the MG Energy batteries, you need to use one of their BMS units. And there are basically two families of BMS. The one I've got in my hand is their low voltage master unit. And then there's a high voltage master, which is for systems that are above 100 volts. So today I'm going to concentrate on the low voltage range of the products. And within that, there's three voltage ranges that are available. There's a dedicated 12 volt unit. There's a model that will do 24 to 48 volt systems. And then there's a further model that will do 72 to 96 volts. The principal difference of them is really just how the control electronics are powered. So the 12 volt unit is basically taken directly off the battery voltage. And within the other two units, there is a DC to DC converter in there to drop the system pack voltage down to a level that's usable by the control electronics within the unit. Within the BMS is a protection contactor, and this is there principally to protect the battery against overcharge or over discharge. It is able also to be used as your main isolation for your system on board, so you can control it manually as well. There are various models of the BMS with different capacities of contactor built into it, ranging all the way up to 1000 amps. So it gives us a lot of granularity of options in terms of the system size and capacity. Ultimately, we end up with quite a lot of variants of the BMS built off of the low voltage overall family, the three different voltage ranges, and then the different capacities of contactors within each of those products. But we can assist you in terms of deciding on the correct specification of unit for your system. So let's first have a look at the external connection points on this unit, and then I'll remove the lid and we'll have a bit of a look at what's inside so you understand how it all goes together. So on my right hand side here, we've got 4 connection points for batteries or strings of batteries. And the positive side of those are fused, negative side goes onto a buzz bar. We can see that in a little bit more detail when we remove the lid and have a look inside. On the left-hand side, we have connection points for your electrical system, either on board the vehicle, a boat, whatever your application is. So that can be anything from lights, pumps, inverters, chargers, cross-charging to other systems, anything of that kind of nature. And again, we have 4 connection points for that. Once again, the positive's fused and the negative going onto a buzz bar. Those two sides of the system are isolated from one another by the protection contactor built into the unit. That protection contactor will work automatically once the battery is on and disconnect in the event of a system problem, but it can be controlled manually to use it as a main battery isolator switch. So if we then look at some of the control connections in the center here, we're going to start with the 2 groups of CAN terminals here. These CAN connections are split into 2 groups. We've got a battery group on my right hand side, and we've got a public CAN network on the left hand side. Each of those networks have got 2 different connector options. I talked earlier about the options that are available on the battery. Both options come as standard on the BMS. So the BMS is standard either way. You just need to choose which connector type you want to have on your battery, and then you can elect to use the cabling system to suit. So we have the RJ45 ports, if you're choosing to use that connector type, and we have the M12 connector ports if you're looking to connect that type. And there's no reason why you can't mix and match. So you could have M12 to the batteries with M12 batteries, and then go off to your system in RJ45. They're just paralleled within the unit. In addition, we have some hardwire connections here. So these hardwire connections are used for things like the remote control of the main contactor, so you've got the manual operation of it, but they also provide some key volt-free contacts for some of the primary functions within the BMS. And this allows us to integrate in with equipment that we can't integrate with digitally. So let me use a bit of an example here. We might have a situation where the batteries are reaching a full state of charge, but we've got a little bit of imbalance and the the BMS is asking the battery charging to be paused. For products that are digitally connected, in other words, they've got a CAN connection and we can communicate with that device over CAN, we can instruct the charger to turn its charging current down or even off, and that will then meet the requirements of the BMS. But we may have a charging source where we can't communicate with it digitally. So in that instance, we have some volt-free contacts which we can access through these connection ports here that can be used to drive a relay or a contactor to turn off that charging source to allow that cell balancing to be completed. So talking in a little bit more detail about these non-digital connections, let's go through them in turn. So we have a 13.5 volt, 1 amp output that is live all the time the battery is live. So this is a great way of powering some other control equipment associated with the battery. We have another 13.5 volt, 1 amp output, which is an allowed to charge signal. So that can be used to keep open a relay by driving the coil of that relay directly. Then we have an allowed to discharge, similar 1 amp output. Then we have an external start button, and this is just a connection which we pull down to ground to actually start the battery. Then we have a status output, so 13.5 volt, but only 140 milliamp, but enough, for instance, to drive an LED lamp, just to give you a visual indicator that the battery is on. And then finally, we have a ground output, which is a common ground for all of those 13.5 volt outputs that we discussed earlier. On the second contact block, we have principally dry contacts. So for each of these functions, we have a pair. First pair being allowed to charge, the second pair being allowed to discharge, and the third pair being a programmable relay that we can effectively assign to whatever function we like. There are manuals for this product on our website, so if you need to have a look in more detail, please feel free to download a copy. The lid of the BMS is loosened with these 4 screws at the end here and the 2 at the base. I've loosened those, so let's get the lid off and we can have a bit of a look inside. If I work from the left of the unit across, what we see here is we've got 4 input channels here for the 4 battery strings, or individual batteries if it's a 24 volt system. Negative connection point is underneath these little plastic shrouds, and these plastic shrouds have a little break off prong here that holds it in place in the event that there's no cable connected. But in the event that you are connecting a battery or battery string to this particular point, literally just a matter of breaking off that tab, and then the shroud is supported by the cable underneath. And this little plastic guard just provides a bit of extra physical isolation between the positive and negative connections. The positive battery connection point goes onto this stud here, and then a mega fuse will sit across these 2 studs. The fuses aren't supplied with the unit, as the ratings of those fuses is going to vary by application. They're a pretty inexpensive part and widely available. So if we move towards the right, we basically just see our other input channels here. And if we follow the negative bus bar across, it looks like we've got a kind of a break in the center of that bus bar, but it's not a break, it's connected with a shunt, and that shunt allows us to measure how much current is flowing in or out of the battery, and that then allows the BMS to calculate the state of charge for the battery. It's important that we calculate that quite precisely because we can't rely on battery voltage. With a lithium iron phosphate battery, the voltage is pretty consistent across quite a significant part of the state of charge of the battery. So it holds at a very steady level, which is great from a performance perspective, but it does mean that you can think you've got a good charge in the battery and then all of a sudden it starts to tail off if you're at a low state of charge. So this gives us much more accurate information on the state of charge, and that is relayed out via the CAN ports that we discussed earlier. If we come across to the positive bus bar here, we've got our main protection contactor that I talked about earlier. The unit in front of me is fitted with a 600 amp contactor, so this is sort of towards the upper end, I guess, of the range. The only unit that's larger is the 1000 amp. And then moving further across to the left hand side, we have our output fuses, positive connection point, fuse that straddles across these studs here, and the corresponding negative connection point for each of those circuits. With the protection contactor, one thing that is important to note is the fact that we have to have a kind of a pre-charge device on this connection. Because a lot of the equipment that you may have connected to these batteries can be quite capacitive, and therefore it takes a big gulp of power when you first connect it, we need to protect against that. The challenge with those capacitive type of loads is that it can cause an arcing across the contacts of your isolator when you first connect it, and that will ultimately lead potentially either to damage of those contacts, or very worst case scenario, the contacts welding, and then the contactor will just be effectively welded closed. It will then be unable to perform its protection function. So the pre-charge device, broadly speaking, is a resistor that sits across the input and the output, and that resistor is connected just prior to closing the main contact, and that allows us to preload those capacitors with energy before closing the main contact, and it protects against that arcing and welding of the contact. For most of our systems, a single BMS works really well. It allows you to connect 4 strings directly. You can connect more strings by commoning them up prior to bringing them into the connection points here. So for instance, if you had 8 strings, you could put a pair to a commoning point and bring from that commoning point, just bring a single input for that pair of strings into one fuse, allowing you to connect 8 strings. But there are larger systems or applications where we need more than one BMS. Sometimes that's just to create us with a bit of redundancy, so that if we have an issue with one set of batteries or one BMS, that we can keep the system live with a duplicate system or a parallel system. Where we're doing that, it's in principle just a matter of splitting your batteries across the 2 BMSs and combining the output of those 2 BMSs together to provide a single supply to your consumers or charging sources. The slight complication is really how we deal with the data and how we deal with the volt-free contacts and signals that I discussed earlier, where we're trying to control charging sources. So now we've got 2 dry contacts that are in parallel, or we've got 2 13.5 volt outputs, and we need to respond to either or both of those. So the solution really is to use the MG SmartLink, and the MG SmartLink allows multiple BMSs to communicate with a single SmartLink, and that SmartLink then aggregates all of that data and provides really exactly the same kind of outputs that we talked about earlier, but for the whole system rather than as an individual BMS and the batteries connected to that individual BMS. So you'll notice absolutely identical connectors. They're marked up the same. We've got the RJ45 connection points, so we can just connect those in with the battery BMSs. And then this becomes effectively the overview of all of the BMSs and then the batteries beneath those. We've talked a little bit about this CAN communication and how that can be used. And ultimately, there are 2 ways of going with the CAN communication. The messaging of this CAN is freely available from an integration document from MG Energy. That will allow you to integrate it in with your system by taking that integration document and listening and responding to those CAN messages. But if you're looking at doing something straight off the shelf, then it's by default fully integrated with the Victron system. And to achieve that, we take the Ethernet public CAN connection here straight into a Victron Servo or other GX device. That GX device then recognizes all of the data that's coming from the BMS and then controls any Victron equipment that's connected to that GX device directly. So it could be a Quattro or a Multi over VE bus. It could be chargers such as a solar charge controller using VE Direct or VE CAN, and it will take the state of charge and the battery data and display that as the primary battery source. So that integration just exists straight out of the box. It's just literally a matter of plugging in that RJ45 connector, and the Victron system will recognize this battery and then will respond to its requirements. I talked earlier about the RS battery behind me, which is the high performance battery from MG. And when I talk about high performance, I'm not talking about its quality or the amount of stored power, just talking really about the rate of charge and discharge that you can achieve with the battery. And that higher performance is really delivered with the RS battery by liquid cooling or liquid warming in the event there's a very cold environment. The LFP product is an air-cooled product, so the performance of that is really dictated by the cooling that we can achieve, which is partly dictated by the ambient temperature. But broadly speaking, what we would normally expect to see is that you can charge and discharge the battery pretty much consistently at what we would call a 0.5C rating. 0.5C means half of the nominal capacity of your battery bank. So if we use an example, for instance, that we had 4 280 amp hour LFP batteries connected here as a 24 volt system, that's going to give us somewhere in the region of 25 kilowatt hours of storage, which means that we would, broadly speaking, be able to charge and discharge that continuously at around about 12 kilowatts. So that gives us a 2-hour charge time, and if we were doing a continuous discharge, a 2-hour discharge time. For most of the kind of applications that we see, this is more than ample, because really what most people are looking for is an amount of stored capacity that's going to provide them with power and lights and operation of all the equipment on board their vehicle or vessel, perhaps overnight or certainly for an extended range of time. And a 2-hour charge period is generally very acceptable. We can provide higher levels of power for a shorter duration, and at the kind of upper limit of that is a 1.5C discharge rating that's quoted as around about a 10-second rating. So in our example, we'd be able to pull 36 kilowatts from this battery bank for a very short period of time, but that's a kind of a curve that falls away down to our continuous rating. So a good example of that kind of that instantaneous rating would be starting up pumps and motors and things like that, or short duration loads like thrusters in a marine application, and then you'd be kind of falling away to limited duration, higher power loads rather than continuous. So microwave kettles, generally heating kind of loads that would be on for a matter of minutes. Well, we can support those at a higher level than our 0.5C, and then we're really then looking at our 0.5C being our background loads, which would generally be lighting, potentially a bit of air conditioning, that type of example of consumer. So to wrap up, the lithium iron phosphate range from MG is great for a whole range of applications. We've got 12 and 24 volt systems, which are great for domestic power on vehicles and small vessels. We're able to move up to 48 volts, which is really kind of starting point for slightly more serious electric propulsion applications. And then we can step into 72 and 96 volt, which takes us into a whole range of other applications, such as portable power for larger pumps and winches, for all kinds of industrial applications. So the product really is suited for a wide range of land, mobile and marine applications. So with lots of different options, we're here to help you put together the right package for your particular application. Contact our team here and we'll walk you through selecting the right products to build up the package to give you the right amount of power, the right amount of capacity to meet the demands of your particular application.